All right. Is it working? Yeah. Hi guys. We did the radar scattering prediction and we put HP. Okay. Okay.
Yeah, you're good.
We put HP first because we're very thankful that he helped us with understanding the whole process of radar scattering prediction. Without him, this team wouldn't exist. So we are very grateful that he helped us. So I want to first thank my wonderful team members here. We're all from different backgrounds, but we had one thing in common, and that was that we didn't know anything about snow. So I'm very glad and I'm very proud of them that we made actually a very good result, as you will see, and that we pulled through this as a team. So what was our problem statement? It was our DMRT Snowpit measurement inputs, such as snow depth, grain size, temperature, and density, sufficient to model backscatter using a machine learning model? And a side project we had was, can we relate DMRT tuning parameters to Snowpit observed variables? And I will come later to that second, but first the first. So we made a custom machine learning model that can predict backscattering from Snowpits. And a machine learning model is actually a black box where you give inputs, and then it will tell you something about the output, which is here, is backscattering, but it doesn't tell you which process is going on. And that's why you have DMRT models that predicts backscatter, but as a physical model in which you can see which processes are going on. We also did an evaluation of the variable importance to see which variables within this black box were the most important ones. And in the end, but that's something we didn't do, but what the end goal was to actually, if you have a physical model, then you can go and do the inverse modeling and go from backscatter to sweep prediction. And that would be absolutely great to have. But we didn't do that because that's way too difficult. It takes probably about 4 years. So what is DMRT? DMRT is a dense medium radiative transfer model that will model the snow microstructure and that will attempt to estimate the backscatter based upon the input parameters you give it. And what are the input parameters that we give it? It's based upon a snow pack that is defined into layers, with each a certain layer thickness, density, temperature, grain size parameter, and a clustering parameter. And this, the dense medium radiative transfer model that we used was DMRT BIC, and the BIC stands for bicontinuous. And that's a model which accounts for volume scattering using a bicontinuous medium to create the snow microstructure. And it has some tuning parameters that are normally calibrated, and those are the grain size parameter, so the zeta, as you can see here, and I'm always pressing the button. That shouldn't happen. So this zeta, what it means is it actually gives some sort of estimation of the grain size of the microstructure, of the snow microstructure. And if you increase the value, then you decrease the grain size within the model. And you also have a clustering parameter B, and that has that shows the clustering effect within the DMRT model. As you can see here, if you increase this clustering parameter, then you see that the clusters will decrease. So those are two tuning parameters that we need to run the DMRT model, but that are not within the snow pits. So you have to find a relation between the snow pits and these tuning parameters.
So for this project, what we did was we mainly used the Grand Mesa data. The data was collected from SnowEx database between January and March 22, and it consisted of about 136 snow pits. After filtering it down, it came up to about 128. We used around 4,784 UAV-SAR rasters and 4 polarizations from the L-band, and also the GPR SWE measurements, which were extracted again from around these pit locations. We had to do a little bit of pre-processing for these snow pit measurements. First one was to select those pit locations which had no tree cover. Then we extracted parameters like the layer thickness, node density, average particle size or the grain size, and the temperature per layer in a pit. We created a table for the DMRT processing, and then we averaged these variables for all the layers for each pit. And this was used as the input table for the ML application.
Okay, so now we'll explore the relationship between the tuning parameters and the Snowpit variables. So what we did, we took a table from literature that linked already the grain size and density to these parameters. So these parameters, the DMRT model was run, and then these parameters were tuned, and then they were linked to a Snowpit location. And as you can see here, we have these regressions that we made. So for zeta, we have a power regression to predict zeta. We use the grain size, and to predict B, we'll use the multilinear regression to predict the B from the grain size and the density. So what we did then, when we had these regressions, is use them on all extracted pit layers that we had, so that in the future, because we didn't do that because we didn't run the DMRT model, but in the future, these pits are ready for DMRT runs. And we can use these DMRT runs to check if this extrapolation actually is possible and if it works. So that's some future work that needs to be done.
Cool. And then going back to so we wanted to model this relationship between the polarizations and the UAV-SAR and the Snowpit data. So to do that, we had to gather those raster images from the Grand Mesa, and we found the ones that overlapped with the Snowpit data that we gathered previously. And then for those, we kind of took just a naive approach, and we just averaged the amplitudes around a 50-meter radius for each snow pit for the separate dates. And then we took the 2 dates and then we averaged those together. This gave us a single amplitude value to work with for each snow pit for each different polarization. So then this gave us the ability to create models for each of these values to see if there's a relationship and to explore that. And so before running a model, we just wanted to kind of look at the features that we had for each snow pit and see what the relationship looked like for each of those different polarization values from the amplitudes given by the UAV SARs. And from this, we saw that there was not necessarily a linear relationship, but some correlation in the difference of the polarizations for sure. And then we saw the biggest correlation in the height and temperature, but you can see the 4 different features that we were looking at. So shows height, density, temperature, and grain size. And then we went a step further and we also looked at the GPR SWE measurements, and we found those the GPR SWE data that was close to our snow pits, and then compared that to our polarization values as well. And we also saw some correlations, but it's a little shaky. So then I'll hand it over to Anu to talk about our models.
So we applied a couple of regression algorithms. The first one was multiple linear regression, the second decision tree, and the third random forest. I'll talk about the first 2. So we applied the multiple linear regression on each of the polarization, and our input parameters were the height, grain size, density, and temperature. And for each of them, we got certain coefficients which told us which parameter contributes to how important that parameter is in the model. This is kind of a snippet of the code for one of the polarizations. And the second model was a decision tree. The decision tree again tells us about what kind of parameters are important and to predict this amplitude. And as you can see, the temperature and density are slightly more important in this case. And again, this is a snippet for just one polarization. And the next one is the random forest.
For our random forest algorithm, we only use 2 trees in this forest because our data is pretty limited. But as we can see from the correlation for each 4 output, though this algorithm is pretty simple, but it have a strong correlation between the predicted data and the actual data. So from this 4 graph, actually you could see that although we only use a very simple model to do the prediction, but we could also see we use the input variable could relate to the actual output. And also we did a variable importance for each input variable in our random forest model, although these have different specific number for each importance, but we could see they have very similar chance for each importance in each model.
Yeah, so our final results were, not necessarily the most conclusive, but there was a lot left to do. It's almost like we were only here for 3 days. The best model fit was that multiple linear regression, and we were able to identify temperature and density as the variables that had the most influence for predicting backscatter. And we were able to identify that that height and grain size were not consistent, if not necessarily insignificant, in importance between different models and polarizations. That's our GitHub below. Yeah, and then just for future work, we want to expand this past, the smaller set of Snowpits that we were using, and then do the thing for 4 years where we actually start to include that transition towards being able to protect SWE from backscatter, as well as including SWE and liquid water content parameters, as opposed to primarily UAV SAR. And that's us with our fearless leader.
Really wonderful job. This team learned a lot to get up to speed to do that. And a lot of you have said, oh, these are inclusive results. You really only had 3 days, right? Monday was kind of figuring out what we were doing. Today was pretty full. It was really only half of each of those 3 days. So think about what you accomplished in a day and a half, and sort of the foundation that has been built for where it's super projects. I have, I guess I'll just allow a question for this group, and then we'll kind of start a wrap up. And I have a message from Greg White. Any questions for this group? Wonderful job. Oh, we do have one.
What was the most interesting thing you learned about snow, since you all said you had numbers?
Good question. It was interesting to learn that there is so much data available, and that we can use so much data to make all sorts of analysis. So that was beautiful.
The fact that people actually go out in the winter and dig these pits and then take all of these measurements by hand to give us these crazy data sets is pretty impressive.
Awesome. Well, we don't have the audio working for Carrie to chat with you here for